There is an old philosophical question about a tree in a forest. If it falls with nobody there to hear it, does it make a sound? If you ask a quantum physicist this question, they might say the sound was there, but you couldn't be sure the tree was, which is a strange answer if you think about it. Quantum mechanics has continuously pushed the boundaries of our understanding of the tiniest aspects of reality. Numerous experiments have revealed that particles behave like waves or can appear to be in multiple places simultaneously. In the quantum world, we can only determine the likelihood of something appearing in one place or another until we observe it, at which point it assumes a definite position. This concept troubled Albert Einstein, who once stated, "I like to think that the moon is there even if I am not looking at it." Since the discovery of the strange behavior of quantum systems, we've had to confront what appears to be an uncomfortable truth. For some reason, it seems that what we consider as reality, the location of objects and their properties, isn't fundamentally predetermined. If you don't measure or interact with your quantum system, it remains in an uncertain state. We can only describe its properties and the potential measurement outcomes in a statistical and probabilistic manner. But is this an inherent limitation of nature, or there's an innate unpredictability until a measurement or quantum interaction takes place? Or could there be a hidden reality beneath what we observe that is entirely predictable, comprehensible, and deterministic? Reality is a complicated thing, especially when it comes to quantum phenomena. Let's start with the most famous example of quantum indeterminism, the Heisenberg uncertainty principle. In the classical everyday world, there is no issue with measurement. You can take any object you like, whether it's a jet, a car, a tennis ball, a pebble, or even a speck of dust. And not only measure any of its properties as you wish, but based on the known laws of physics, we can predict those properties far into the future. All the equations formulated by Newton, Einstein, and Maxwell are entirely deterministic. If you provide the positions and motions of every particle in your system or the entire universe, scientists can accurately tell you where they will be and how they will move at any future moment. The only uncertainties we encounter are due to the limitations of the measurement tools we employ. However, in the realm of quantum physics, this is no longer the case. There exists an intrinsic uncertainty in how precisely you can simultaneously determine a wide range of properties. If you attempt to measure, for instance, the position and momentum of a particle, the energy and lifetime of a particle, the spin in two perpendicular directions, the angular position and angular momentum of a particle, you will discover that there is a limit to how accurately you can know both of these properties at the same time. The product of these properties cannot be smaller than a fundamental value, which is proportional to Planck's constant. In fact, the instant you measure one such quantity to a very fine precision, the uncertainty in the other, complementary one, will spontaneously increase so that the product is always greater than a specific value. Traditionally, we've viewed the quantum world as inherently uncertain, and this uncertainty can't be entirely eliminated. When you precisely determine a property like the spin of a particle in one dimension, the uncertainty in perpendicular dimensions must increase without limit to comply with Heisenberg's uncertainty principle. In essence, you can't cheat the uncertainty principle. Meaningful knowledge about the actual outcome of a quantum system can only be obtained through measurements. However, there has long been an alternative concept, the idea of hidden variables. In a scenario involving hidden variables, the universe is fundamentally deterministic. Quantum entities have intrinsic properties that could, in theory, allow us to predict precisely where they would end up and the outcome of any quantum experiment in advance. The catch is that some of these governing variables are beyond our ability to measure with our current understanding of reality. If we could access and comprehend these hidden variables, we'd realize that the indeterminate behavior we observe is essentially a product of our lack of knowledge about what's truly happening. With a full understanding of these underlying variables, the quantum universe would appear far less mysterious. One of the greatest physicists of the 20th century was John Wheeler. Wheeler was thinking about this quantum weirdness, about how these quanta sometimes behave as particles and sometimes as waves, when he began to devise experiments that attempted to catch these quanta acting like waves when we expect particle-like behavior, and vice versa. Perhaps the most illustrative of these experiments is shown passing a photon through a beam splitter and into an interferometer, one with two possible configurations, open and closed. Interferometers function by directing light in two different paths and then recombining it at the end, creating an interference pattern based on the difference in the path lengths or the time it takes for light to travel through the two routes. Wheeler's curiosity led him to wonder if these photons somehow knew in advance how they should behave. He would commence the experiment in one configuration, and then, just before the photons reached the end of the experiment, he would either open or close, or not, the apparatus at the end. If the light had pre-knowledge of what it was going to do, you'd be able to catch it in the act of being a wave or a particle, even when you changed the final outcome. In the realm of the physical universe, it's crucial to remember that no matter how confident we are in our logical reasoning and the soundness of our mathematics, experimental results are the ultimate judge of reality. When we conduct experiments and attempt to derive the governing rules from them, we must arrive at a consistent framework. While there are numerous interpretations of quantum mechanics, all equally successful in describing reality, none have contradicted the predictions of the original interpretation. Preferences for one interpretation over another, which many people have for reasons not easily explained, essentially boil down to ideology. No matter how uncomfortable it may be, there's a certain level of weirdness inherent to quantum mechanics that we cannot eliminate. You might not find the idea of a fundamentally uncertain universe appealing, but the alternative interpretations, including those involving hidden variables, are in their own manner equally peculiar. When we look out at the universe today, it simultaneously tells us two stories about itself. One of those stories is written on the face of what the universe looks like today, and includes the stars and galaxies we have, how they're clustered and how they move, and what ingredients they're made of. This story has two parts. The first part is about the universe we see around us, which we understand by just looking at it. The second part is about how the universe became the way it is today. Figuring this out is a bit more complicated. We can study things far away to learn about the distant past, like when the light we see today was first produced. But to truly understand it, we have to use our scientific theories, like the laws of physics and the Big Bang Theory. When we do that, we find strong evidence that before the Big Bang, there was something called cosmic inflation. However, to make our observations match our theories, we have to accept the idea of a multiverse. That's why many physicists believe in the existence of a multiverse. In the 1920s, scientists found strong evidence that the many spirals and elliptical shapes we see in the sky are not just individual stars, but are actually whole galaxies. They also noticed that the farther a galaxy is from us, the more its light gets stretched to longer wavelengths. At first, there were different ideas about what this meant, but as more evidence came in, only one explanation remained. The entire universe was getting bigger, like how dough with raisins in it expands as it bakes. If the universe is getting bigger today, and the radiation in it is shifting to longer wavelengths and lower energy, then in the past, the universe must have been smaller, denser, more even, and hotter. When we consider that matter and radiation are part of this expanding universe, the Big Bang Theory leads to three clear predictions. There should be a vast cosmic network where galaxies grow, change, and group together more as time goes on. We should find a background of low-energy radiation that remains from the early universe when neutral atoms first formed in its hot state. The proportions of the lightest elements, like hydrogen, helium, lithium, and their different forms, should be consistent, even in areas where stars have never formed. All three of these predictions have been confirmed by observations, which is why the Big Bang Theory is the leading scientific explanation for the origin of our universe. It has outperformed all competing theories. However, it's important to note that the Big Bang Theory only describes the very early stages of our universe. It doesn't tell us why the universe had those characteristics.